Hello everyone, I am Hassan and today I will be presenting our paper. To get us started, I would like to walk you through an interesting experiment called the Chinese room problem, where you have to imagine that you are this guy and your job is to deceive me to believe that you actually know how to read and write in Chinese. So what I do is to give you a letter, for example, it says, "How are you?" in Chinese, and what you have there is a big Chinese book where you can go through and do some statistical analysis and find a plausible answer, such as "I feel wonderful." But when I say "How are you?" in Chinese, because I know Chinese, it comes with a meaning and a purpose. You, on the other hand, just playing around with symbols, and these symbols are not connected to any meaning, so you have no idea what you're talking about. And the meaning and interpretation of your response comes again from my side. And that's the problem we're trying to address, that many state-of-the-art NLP models purely rely on text. So there is no way that they can actually draw meaning from the symbolic representation of the language. And here in this paper, we focus on visually grounding the word embedding model. The way we train this word embedding model is very similar to the Chinese room problem, where we set up a network and train it on some language model task. Here, the network tries to fill in the blank and find some adjective for the word cat. And because both big and small satisfy the criteria, after the training, they end up in the same vicinity of space, even though they mean different things. And if you simply ask the network why it can, or if I one day break into the room and tell you, hey, these are two different things, you can simply say, I don't care because I was trying to deceive you, and that's all. And here, the same. The network tries to complete the sentence, and that is all. So there are many ways of connecting this textual representation to the real world through images. So given the word vector t and this corresponding image vector v, some approaches learn a mapping from t to v and call the vector at the end the grounded version of that vector. Other approaches project both modalities into the same space and force them to be similar or dissimilar based on some criteria. Our approach, on the other hand, tries to ground the embedding implicitly. So, meaning we want these modalities to be separated, however informed and aligned with each other. So we want to use the relationship of the object in the images and to inform the textual embedding about the real world. In other words, we want the textual embeddings to be aligned with the image embeddings. So here's the architecture of our network. We have TE, a per-trained textual embedding, either FastText or GloV. And we also have the mapping matrix M, whose job is to ground the word embedding TE. So after the training, we simply plug in any word and get its grounded version as the output of the mapping matrix. And the textual embedding here, it could be any word. It could be an abstract word or out of the vocabulary word. So the way we align this textual embedding to the images is by training the network on 3 tasks. We have two language model in different direction, and also a binary classification one where given a sentence and an image, it decides if the sentence describes the image or not. Here the mapping matrix basically encode the word embedding into the grounded space where the image information is fused using 3GRU and then decode back into the so-called textual space. And as you can see, the network is restricted by using its transpose of the mapping matrix and the embedding. So this way, the information that is already there is preserved, but at the same time, we want to align the embedding to the images. And that's the point of our paper. We have evaluated our grounded embedding on many benchmarks. Here is an example of similarity lexicon where the task is to estimate the similarity score of a pair of words. And this data set is categorized into different categories such as highly abstract and highly concrete words. And as you can see, our approach manages to not only brings improvement for concrete words compared to GloV, but also enhance the performance of highly abstract words. Whereas if you compare it to other approaches such as picture book, you can see that their performance is highly biased toward concrete words and kind of lose the information of abstract words. Looking up at the nearest neighbors also reveal interesting properties. For example, if you take a look at the so here G means textual embedding from glove, and V is our grounded version of glove. So for example, for the word big, you can see that glove brings little, an antonym of big, but however ours brings big with capital B and humongous, and also same with the word smart. We have dumb in the same vicinity of the textual space. However, in the grounded space, we have more similar words. So the antonym problem is kind of alleviated here. And also similarity is prioritized. For example, for the word horse, the textual embedding brings dog, riding, and donkeys, which are related but not very similar. However, ours brings steed and racehorse. And also, typos are magically in the same cluster. These typos occurred with different frequencies in the text, so they are gradually pulled apart. However, our grounding, our mapping, puts them again in the same cluster. We also evaluated our embedding on sentence level task. Here the task is to estimate the similarity score between two sentences, and there is no training data, so it truly measures the generalization power of each embedding. You can see the performance of per train glove. On the first row, on the last row, you can see the performance of ours. Overall, considering the mean score, we boost the performance up to 10%. And we also did an interesting experiment where we resume updating the glove embedding on the captions only without any images. And even though we still get some improvement, but it's not comparable to the case where we have the images involved. In conclusion, we can say that visual grounding benefit highly abstract words as well, and it seems to prioritize similarity over relatedness, even though it also boosts the performance of relatedness. And with the antonym problem and typos example, we saw that it seems to refine the irregularities of the textual vector space. Overall, it seems like a promising idea not to mix these two modalities together, but have them inform and align with each other. In the future, we would like to extend our work to sentence-level visual grounding and explore the potential benefit of using our embeddings in transformer-based language models. Thank you very much for your attention. Feel free to check our paper out if you're interested.